Hello everyone, we are Team 40. Today my team and I are going to present our project on improving autonomous vehicles using semantic segmentation. Our presentation will include the following, shown on screen, along with a demo at the end. Let's move on to our project background. Have you ever wondered how car companies such as Tesla achieve such precise autonomous driving? This is the focus of our project is a safe and efficient driving experience for autonomous vehicles. And the method we wish to achieve this is through semantic segmentation. So what is semantic segmentation? It is essentially classifying an image on the pixel level. You can see above that every single pixel has a color assigned to it, where classification is done object by object. Semantic segmentation inherently captures more information about the scene due to its finer pre-pixel classification. This richer semantic information allows vehicles to understand the environment to a greater degree, which is why we are focusing on semantic segmentation. But what is the problem we are focusing on exactly? Autonomous driving has been a primary focus and area of development for Toronto's transportation environment. Therefore, we aim to contribute meaningfully to this field to develop a segmentation model tailored towards Toronto. Given the unpredictability of cityscape with varying objects, weather conditions, and environments, this task may be more difficult or simple than we expected. We did our best to address these nuances.
The dataset we have chosen to work with is a Cityscapes dataset, which is a very prominent open source dataset. It was gathered in 50 European cities and it comprises 19 classes of objects you'd very commonly see in cities, shown here. However, there's a problem with this dataset. The reason is because it was collected in European cities, most of your buildings are European. They're old-fashioned, and kind of different from those you'd see in Toronto. So we decided to augment this dataset with our own. We collected our own data all over Toronto, trying to capture as much nuance as possible. After collecting this data, we had to annotate it very meticulously, according to the Cityscapes data labels, as you can see here. However, we decided this was not enough. Because of the time-consuming nature of collecting and annotating data, we only had around 83 of our own data. Therefore, we decided to augment our data further using the mapillary dataset, which is very similar to the Cityscapes dataset. However, it has images from all around the world. Therefore, we selected those that were the most closely related to Toronto and made them into our own dataset. Because the mapillary dataset does not have the right color scheme, we also had to meticulously convert each of the images to the same data scheme using 20 data classes such as Cityscape. In the end though, another thing we've had to do is extract the labels. Because the cross-entropy function does not expect an RGB image, we had to turn it into a grayscale image where each pixel is the class label, an integer. We split the data into train, validation, and test sets, and the split we went with was 80, 10, and 10 because of our smaller size. We only had around 3,000 images, therefore an 80, 10, 10 split is most likely appropriate for our cause.
Here is our baseline model, a UNet architecture, which is a very widely accepted architecture for its effectiveness and semantic segmentation tasks. We have implemented and trained a UNet model from scratch. Here is our main primary model. It's also encoder-decoder network, but with a vision transformer taking position and patch embedding as input, and where patches are partitions of an image, and they are fed to the transformer encoder layer, which produced an embedding. This embedding will be fed into our decoder network, shown to the right. Now for the decoder, it's mainly implemented based on the Cedar paper or segmentation transfer that achieves really good results. Our goal here is to fine-tune this decoder only on our data images, which are the ones we talk about from the mapillary dataset in order to achieve good results. We have tried a parallel convolution network from the Deep Library 3 Plus paper along with a skip connection, which is very common in segmentation networks, along with a sampling network towards the end. However, we have decided not to use this as our final network for reasons will be explained later.
Here are our training curves for fine-tuned model. We only used the data we collected and mapillary dataset because the trained parameter loaded in were already trained on the Cityscape dataset. This greatly limited the number of images. After fine-tuned for 10 iterations, we see that there is no sign of overfitting. Here are two graphs of training curves for new decoder. The reason why we could not use our custom decoder is because the parameters were randomly initialized and we had to use a large dataset with all the Cityscape data. Unfortunately, Google Colab simply could not handle this amount of training. Even when we bought more compute units, we were only able to get maximum 20 epochs. before everything just broke down. But as you can see from the training curves, we predict that although the training curves are noisy, we could get a comparable performance to our fine-tuned model. Next, we want to introduce accuracy as coefficient and intersection over union. These are all common metrics for segmentation tasks evaluated on dataset. As you can see, our primary model outperforms our baseline model, which is a good sign that our model is performing well on every metric.
These quantitative results are backed up by the qualitative results. As you can see, given these raw images, the segmentation map looks pretty similar to what you would expect. However, in terms of what things discussed, you can see that the border of projects sometimes are not quite easily mapped. This corresponds with the fact that in the side before the intersection over union matrix, which measures the spatial locality and how much the object border and the borders of the end object are well defined, is the lowest out of the three matrices.
Now let's begin our demo. Let's say you want to segment a car's input video extracted as frames as seen on the left. What you can do is you can take the first frame, copy its path, put it down here, and run it through our model, and you'll see the output segmentation map. Now assume you can repeat what we just saw in the video throughout the entire frame at a high enough frequency. What we can see is a video, essentially a segmentation map of the person moving through the screen, which is exactly what a car wants to see and needs to see to make good choices. Now for our takeaways on what we learned. We learned that a good data set is definitely the most important thing to training any model, and we also learned the ins and outs of implementing very complex models such as transformers and U-Net. Finally, we always have to keep in mind time and compute limitations when training or designing a model.